In today's lesson, we are going to solve and graph one-step absolute value inequalities. We've been working a lot with absolute value in equations. Today, we're going to change some of those symbols to work with inequalities. So let's go ahead and review some of the things that we already know. We know that absolute value just means that we're looking at a number and a distance away from zero. So for example, if I have the number 4, I need to count how many units away from zero that is. The absolute value of 4 is 4. We also need to remind ourselves that absolute value is always positive. So if we have an equation that is negative, then that means there's no solution. And we know that the notation that we use for absolute value has the double bars around the expression. So we also want to review that in order to solve absolute value equations, there are actually two situations that is true. So for example, we have the absolute value of a plus 8 equals 10. So we're asking ourselves, what are the values of a plus 8 that will get me a distance of 10 units away from 0? We know that the number positive 10 is 10 away from 0. We also know the number that negative 10 is also 10 units away from 0. And we set whatever is inside, bounded by the two absolute value bars, equal to those two values that we've identified has a distance away from 0 of 10. So once we have set up these two situations, we can then go ahead and solve. We want to keep this formatting in mind when we're working with inequalities. The last thing that we need to realize and remember is how to graph inequalities when we're given a final statement. We know that when we're working with exclusive inequalities, we're graphing with open circles. Exclusive inequalities are examples where we have the greater than sign or the less than sign. Contrastly, we have inclusive equations that use closed circles. And we know that we have an inclusive equation if we have something in the expression that includes equal to. So less than or equal to, or greater than or equal to. So let's go ahead and take a look at each of those graphs. So if we want to make an open circle, we would then find the value of -3, and we make an open circle on that value. Since it's values that are greater than -3, greater signals that we need to go to the right. For inclusive, we have a closed circle, so let's go ahead and label our -3, and we're going to create a closed circle. That means we have a dot. And since it's less than, we have to move in the left direction. So let's go ahead and keep those review concepts in mind as we apply them to solving absolute value inequalities. So let's start simple. We're going to first ask ourselves, what does it mean to look for the absolute value of inequalities that are greater than 6? For this example, we have the absolute value of k is greater than +6. So what does that mean? It means that for all values that are represented by k, which values would have an absolute value that's greater than 6 units away from 0? So let's just take a look at random numbers. So I picked -2. I'm going to ask myself, is the distance or the absolute value of -2 greater than 6? No, because the absolute value of -2 is just 2. Let's try -8. We have -8. The absolute value of that is positive because it's 8 distance units away from 0, and 8 is definitely greater than 6. Let's try some of the numbers on the positive side of this number line. We have, say, the number 7. The absolute value of 7 is 7, and we know that 7 is greater than 6. So how can we keep that in mind when we're trying to break this equation or this expression into two different situations? So we're bounded by these absolute value bars, which means that if we were to take them away, we just have some value of k, and we know that already there are two situations. So if we are working with numbers on the positive side of our number line, we know that all numbers that are greater than positive 6 would fulfill this. So greater than positive 6. And with our example earlier, we noticed that negative 8 seems to also fulfill this equation or expression, but numbers like negative 2 do not. So I'm thinking to myself, what if we're looking at the number negative 7? Does that fulfill this equation? Is it true? Sure, because the absolute value of negative 7 is 7. That's greater than 6. How about negative 9? That works as well. Negative 6? No, it seems that negative 6 is only exactly 6 units away from 0, and 6 is definitely not greater than 6. It's actually equal to. So it seems that values for k that are less than or smaller than negative 6 seems to work for this equation. So I know that in order to graph this equation, I need to include all values, open circle because it is an exclusive equation, that are greater than 6, and all values that are less than negative 6. So open circle again because it's an exclusive equation, and since we're less than, it's moving to the left. So values that are included along this arrow on both sides of this equation would make this statement true. So to generalize, the difference between these two situations are the signs. One goes in one direction, while the other points to the opposite direction. And what we also know that is opposite is the value of 6 and the value of negative 6. So it looks like we can generalize that the signs are changed as well as the inequality. So let's apply that to another example. We have m plus 12 is less than or equal to 20, and we're looking at the absolute value of those two equations. Let's go ahead and break them down into two separate equations. So we know that whatever inside those absolute value bars must have some distance that is either less than or equal to 20. So we know m plus 12 is less than or equal to positive 20. And thinking about those rules and generalizations that we made from our previous problem, I wonder if we can make the equation m plus 12 by switching our inequality symbol to be greater than or equal to negative 20. So once again, I switched the direction of my inequality symbol and I made my value the opposite. Then once we're here, we can go ahead and solve this. We need to subtract 12 from both sides to balance this equation. So we have m is less than or equal to positive 8. And we're going to do the same thing for this equation and subtract 12 on both sides. We have m is greater than or equal to negative 32. So what does that look like on a number line? So let's go ahead and graph. We have the number 8. 8 is to the right of 0, if we need a reference point. And then negative 32 is to the left of 0. They're both inclusive statements, so we're going to use those closed circles. So I'm going to go ahead and create closed circles on my two values. And I noticed that in one statement, m is less than negative 8, so we need to move to the left. But then on the other equation, we need to be greater than negative 32. So it seems that in order to graph this inequality, we're connecting the two dots between these two boundaries. I would like you to go ahead and practice and give a shot at this problem we have the absolute value of g divided by 3 is greater than 4. I want you to think about two things. The first, what are my two inequalities? What are my two separate situations? And the second thing I want you to remind yourselves is, how are the symbols in your two equations? And how are your signs? Are they positive or negative? When you're breaking down into two separate inequalities, what do you end up as your inequalities, and how are their symbols and their signs? When you set this up as two separate situations, you're going to be able to use inverse operations to then solve for an answer. And once you arrive to an answer, you can then approach this problem by graphing it. Why don't you take a moment to solve this problem? If you solved it correctly, and if I solved it correctly, it seems that the answer is g is greater than positive 12, and g is less than negative 12. So if we graph those 2 points, if you need a 0 as your reference, we have positive 12 on the right and a negative 12 on the left. Less than negative 2 means we're moving to the left, and it's an open circle. Greater than positive 12 is an open circle, shaded to the right. Now, here's your turn to solve on your own. Now, I want you to keep thinking about those two things that we used to solve the previous problem. But remember, when we were solving equations, what do we do if there's something on the outside of our absolute value expression? And take a look at this symbol. Once you solve this problem, I want you to compare it to, what if I have the absolute value of d divided by 2 is greater than or equal to 4? How will the answers look differently? Once you solve that, challenge yourself with this problem. Good luck.